Thank you very much. And Coach Steve, the floor is yours. You're going to tell us about error detection and correction. Here, we'll start Yoshi over here.
So as you have just noticed, they have nothing but the strongest professors at this institution. You read the title without any trouble at all. Does anybody have any trouble reading this? My spelling is atrocious, I will admit to that. Any parts that give you some trouble? So here, the main theme of the talk is about applications of really simple mathematics. And the slides, as well as the video, will be posted online sometime either later tonight, or if I'm doing too much preparation for the 75,000 steps that a bunch of us are doing tomorrow, sometime on Monday, because Sunday will be for recovery. All right, so fixing this is not too much of a problem. In fact, I gave this talk a few years ago at MathFest, and when I submitted the abstract and the title, they accidentally corrected everything, thinking it was a mistake. And then I realized, oh, wait, you probably meant that as your title as to what was going on. Okay, so how many people have seen anything about error detection, error correction codes? How many people have experience with them? Okay, you all do. You may not know it, but it's going on in the background all the time. And the reason this is so important is this is now the digital age. You know, as the pandemic showed us, when we have to close in-person stuff and move remote, we have ways to transmit massive amounts of information in reasonable amounts of time. And so in a lot of encryption or just a lot of transmission, rather than transmitting letters, we instead transmit numbers. And the advantage of transmitting numbers is we can use math to combine them, to do things to them. And so, for instance, if we use bits of 0 and 1, you might have A as all zeros, B 00001, C 00010, and so on and so on. And so as we're transmitting messages, you know, if you're doing encryption, you want to do it in such a way that only the desired recipient can actually interpret the message you're sending. If you're doing streaming video of something from YouTube, you don't really care necessarily who's watching it. You just want to be able to transmit it so that anybody can read it. And so you want to ensure that the correct message is received. And so the question is, what can you do to maximize your chance that the person who receives the message receives what you intended to send? And so we're going to really focus on that part today, ensuring that the correct message was received. Okay. Out of curiosity, how many people have seen RSA before? All right, so a good number of people have seen RSA before. I'm not going to go through all the details slowly about RSA, but basically by using primes, we can set up a system where people can communicate securely. And what you do is you choose two large primes, P and Q, for the interest of time and just having numbers we can look at. For me, large prime means 5 digits, but in practice, 200 digits or more. We choose some number D. We make public the number N, which is the product of the two primes, and we choose a secret. We keep D secret, and we make a number E public, such that E times D has a remainder of 1 when you divide by P minus 1, Q minus 1. So if you haven't taken a class in abstract algebra, this is just clock arithmetic. If it is, let's see, 5 o'clock right now, what time is it in 8 hours? It is 1 o'clock. So you've just told me 5 plus 8 is 1. Yes, on a clock. And so the only difference is now this is a clock where the number of hours is P minus 1 times Q minus 1. And the way it works is you take your message, which will be a number less than N, and you raise it to the eth power. It's actually a very interesting question as to how can you raise something to 10 to the 200th in a reasonable amount of time. And then you transmit that, and then to decrypt it, the person raises it to the dth power, and amazingly, you get back what you started with. Now imagine instead, you don't get quite the message you wanted. You received 1 digit off. Well, if we do some of the old encryption, which you may have seen before, where we send, maybe a permutation cipher, A goes to Q, B goes to Z, C goes to W, something like that. If you have a few letters wrong, it's not a big deal. You can figure it out very easily. I think most people had no trouble deciphering what my title was from looking at it. But here, if we have just 1 digit wrong, when you try to decrypt it, we only have 2 digits right. So are you surprised that we had 2 digits right out of 1, 2, 3, 4, out of 9? Does that seem reasonable? So why is 2 out of 9 reasonable? Yes. Yeah, if you're doing it at random, if you have 9 digits, you expect to get 1 out of 9 right. So this is within 1 of what you would expect by randomness. So essentially, when we try to decrypt the message with 1 bit wrong, it's complete garbage. It's essentially at the level of randomness. So this should drive home how important it is to be able to transmit information and make sure that the person receives what you mean to send. Okay, so again, we are going to be concentrating on ways to detect and correct errors. And it's absolutely amazing that there are simple algorithms that will not only tell you when you're doing something wrong, but what the right answer should be. It would be wonderful if we had stuff like that when we were taking exams or doing things like that in life. We might have the detection method, but we don't necessarily have the correction method. So we'll talk about a few different ways. So the first thing I want to talk about is the check digit approach. Has anybody seen check digits? Where have you seen check digits? Okay. Anybody else? In where? In barcodes. Excellent. So barcodes is one of the greatest places. In fact, I think it's one of the greatest inventions in the 20th century. The scanner at the supermarket or the store that reads the item and tells you what the price is. Now, every now and then, when you try to buy something, you scan it and it doesn't work. And so you go ballistic and you start destroying things in the store, right? Starting with the person at the scanner and working all the way up to the manager and then corporate headquarters. No, what happens if it doesn't scan? You scan again. And maybe it's just not your day and you try 3 times, or the person tries 3 times, it's not one of those self-checkout lanes, and it just doesn't work. Does that mean you can't buy the product? No, what happens? Yeah, you enter it manually. So the whole point of the check digit is there are many situations where we want just a quick test to see, did we read it properly? I'm buying this candy bar, it shouldn't be coming in at $314. I want to just do a quick check and see. An example where this is not possible is, imagine you are the commander of an attack sub and your position is supposed to be secret, so you may only surface at certain well-defined times, and that's when you can receive messages from headquarters. And so if you get a garbled message, you can't easily ask them, hey, can you please retransmit? So a lot of times it's not easy to get another copy of what you're doing, and you need a way to very quickly detect, have you made an error, and just get the new information immediately. Other times, if it's easy to just do it again, it's fine, just let me know. And so, scanner at a supermarket. So what we're going to do for the talk today is pink, and it looks like it's actually staying pretty close to my colors on the screen here. It's a little bit darker. The dark pink is going to be bits of information. So this is the message I want to send. The blue is always going to be the check digits. And I'll do things initially base 10 and base 2. So why am I doing things in base 10 and base 2? Wait, who's speaking? All right, could you raise both of your hands? Okay, yes, okay, so why are we doing things in base 10?
Well, base 10 is good for people, base 2 is good for
computers. Good, base 10 is good for people. We have 10 fingers. Does the universe care that we have 10 fingers? You can prove this. You know this much about the universe that you can prove the universe. That's beyond my pay grade, okay? I'm not going to say what the universe cares or does not care about. For me, base 2 is much more natural for the universe. On, off, yes, no, true, false. Ohio State, Michigan. Given that I was a postdoc at Ohio State, we may be a little bit on other sides of that at some times of the year. What other bases are good? There's 2 other good bases. I'm sorry. Well, I mean, hexadecimal and all that stuff, it's still really base 2. It's just like a fancier base 2. So there's 2 other good bases. E and 3. Base 3 is actually more efficient for disk storage than base 2. But base 2 with binary search has a lot of advantages. So the check, base B is, yes. For those of you who have done research with me on Fibonacci numbers, the golden mean is actually very useful for some bases. I'm happy to talk about that afterwards. So the way these scanners at supermarkets work, or a lot of barcodes, is the final digit is set up so that the sum is a multiple of 10 if you're using numbers 0 through 9, or a multiple of 2 if you're using zeros and ones. And so if you add up the numbers and it's not a multiple of 10 or 2, what do you know? There's a mistake. What if you add up the numbers and it is a multiple of 10 or 2? What do you know? Yeah, it's the shrug your shoulders. It might be okay. We don't know for sure, but it at least passes the test. So hopefully we are in a situation where errors are rare. If errors are extremely common, then it's going to be very hard to communicate anything. So it's unlikely to have an error. It's extremely unlikely to have 2 errors. And for the most part, I'm not even going to worry about 3 errors. Okay, if we were not in a situation like that, we would have to do something else. All right, so if we look at this example over here, what can you tell me? There's an error. Is the error in the information I care about or in the check digit? We don't know. If it's the actual numbers from before, 91343 for the top, 92343 for the second, okay, we see that the error was in one of the data digits we care about. For the second one, 11011, going to 11010, we see the error was actually in the check digit. And so in the second case, it's actually really annoying. You actually transmitted the message correctly, and it was the check digit that had the error. So in a situation like this, this is really good for quickly telling if you've made a mistake, but not where it is and how to fix it. So not surprisingly, there are a lot more involved methods. If you want to look at some additional readings, you can click on these from the slides. And so some of the other types of errors you could have is you could flip 2 digits. Does anybody know what TEH means? Yes. The, yes, it's the misspelled when you're typing very quickly. And so there's a lot of transpositions. And so there are algorithms that allow you to detect when have you not just put the wrong digit down, but maybe when you've switched the order of 2 digits. Okay, so we want to detect where the error is. So one really good system is called the tell me twice. So what you're going to do is whenever you want to transmit a bit of information, you will always transmit 2 bits. So your number and a check digit. And so you will only send 1, 1, and 0, 0. So if you ever receive a 1, 0 or a 0, 1, you know a mistake was made. If you receive a 1, 1, it's possible that I meant to send 0, 0, but if errors are rare, the probability that both of them were flipped is going to be extremely small. So you can be pretty comfortable if you receive a 1, 1, that 1, 1 was meant. If you receive a 1, 0, we can't correct it, but we at least know that there's a mistake there. All right, so there's a simple way to try to fix it. Anybody ever see the movie Minority Report or read the book? Or this, I guess it was a short story by Philip K. Dick. Okay, so one person? Excellent. So can you briefly summarize it or should I try? Okay.
Where they have these 3 people called pre-songs who predict murders. And it turns out that actually.
Okay, so we don't give away too much. Don't give away too much. That's a good place to stop. So there are 3 precognitive psychics. And so the idea is if 2 of them are right, the 3rd one is probably the one that's wrong. The military uses this a lot of times in battle situations. You have 3 computers that determine how should you fire the weapon. And if 2 out of the 3 give you the correct targeting solution, that's probably the one that's right and go with that. So we'll do a majority rules. So we will only send 1, 1, 1 or 0, 0, 0. So the advantage of that is if 1 error is rare and 2 errors is damn rare, it's a technical term, that if you receive 1, 0, 1 or 1, 0, 0, how would you correct each one? Yeah, first one would be 1, 1, 1. And the second would be 0, 0, 0. So the advantage of tell me 3 times is not only are we able to detect the error, but we can correct the error. Why might this be a little bit of a problem? Why might you not be thrilled about this system? Yes.
I want a 1 gigabyte movie.
You want a 1 gigabyte movie. Um,
And you told me to download 3 gigabytes.
and I've told you to download 3 gigabytes. So this is a situation where the older you are, the more important this problem is in your life. Because right now, your streaming video is not that bad. In the old days, we actually used to buy DVDs, movies, songs, books. Now everything is downloaded. And it used to take a long time to download things. And the worst thing would be is if you download an entire file that was maybe a gigabyte, and then when you're finally down with it and you have everything, it doesn't run because some of the bits were corrupted. So you want to be fixing things as you go, so you don't have to download the whole thing all over again. So the advantage of this is we can correct the errors as we go. The disadvantage is only 1/3 of our message is information we care about. Now, this is not that much of a problem right now because things are now so fast that we can actually deal with inefficiencies of this level. One of the greatest, I think, scientific achievements of the 20th century was the Grand Tour. Does anybody know about this from NASA? Every couple of 100 years, the outer gas giants line up so you can launch one probe and hit all of them. The only problem was, since it only comes up every couple of 100 years, you don't really have much flexibility as to when you can launch. And so NASA had to launch their probe before they were ready to launch it. And so they did the only thing they could. You can't miss the launch window. So they launched the best thing they could, and they were basically upgrading it billions of miles away. And so in a situation like this, you only have so much information you can be transmitting back and forth. If you're losing 1/3 of your message, for information, that is significant. And so you want to be able to transmit information efficiently and quickly. So this is a democracy. What do you want to accept as the minimum level of information percentage in your message? What percentage will you say, if you can do that, I'm happy? Anything below that is just, 1/3 is disgraceful. $70? So you think 70 is the minimum? I think there's a very natural minimum that's lower than 70. 50. Why 50%? Half and half. So in fact, let's do anything above 50 is a success. I'll still consider 50% a failure because I have half information, half non-information. But if I can break 50%, then I'll say I've done something. So I like to have talks with open problems. So there will be some open problems related to what is the best way to do what we're going to talk about. So I don't know if the answer is known in all the cases. So if anybody's interested in trying to explore some of these later, please let me know. All right. Any Seinfeld fans? I'm going to risk asking this. All right, there are 2 beautiful clips. So we are crucially using the fact that we're working base 2. Could we do this if we were working base 10? If we know we made a mistake, could we correct it? No, because there's too many alternatives. But base 2, if it's not 0, what does it have to be? 1. If you were transmitting information, what would be your dream percentage for accuracy? 100%. Do we all agree that 100% is the best transmission frequency? What's the worst you could be doing? No! Sorry if anybody was sleeping. 0 is not the worst you can do. 50% is the worst. Why is 0 not bad? Yes. Yes! In a binary system, if you know it's wrong, you can flip it. So there are 4 main characters in Seinfeld, like other TV shows that often have 4 main characters. And so one of the characters, the best way to describe him is a loser. Everything he does is bad. And he has one episode where he's lamenting that every choice he's made in life is wrong. And so his friends convince him, well, if everything you've done is wrong, the opposite of what you do must be right. Now, normally in life, this should not work because there's more than 2 alternatives. There's a beautiful scene where he's now interviewing for a job at the New York Yankees, and he meets the owner, George Steinbrenner, who goes, "It's a pleasure to meet you." And how would you normally respond to that? Likewise, his response is, "I wish I could say the same." And he ends up getting the job because he distinguishes himself from every other kid. He goes, "You're not like everyone else we've interviewed." So we are crucially using the fact that there are only two alternatives. We are exploiting that tremendously. Right. And so we are going to decide that a success is going to be at least 50%. Now, I'm not going to go into great detail. The natural generalization to tell me 3 times is to tell me 4 times. You're more likely to, correctly fix things or tell me 5 times, but less and less of your message is going to be the data that you care about. So just generalizing to tell me n times is very bad. You will have high degree of accuracy, but at the cost of a lot of storage, a lot of extra transmission. I believe, however, that this is how CDs and DVDs operate, is they have a tremendous amount of redundant information. They really want to make sure they have a good quality playback. And so because they can store so much information, it's not a problem to tell me 16 times, that beautiful hexadecimal system. All right, so let's do some things geometrically. I'm going to revisit the tell me 3 times. And I'm going to write it in 2 different ways. The first is a straight line with my red data bit and then my 2 blue check digits. And then the other is in, I don't know, maybe a triangle, maybe not quite an oxygen, not quite a water atom because of the angles, but something like this. Now, why is this useful? Well, if I look at the first column, they're both going to be 1s or both 0s if it's correctly transmitted. If I look at the first row, they're both going to be 1s or both 0s if it's correctly transmitted. So if I look at the first column, which I guess the only column, and it doesn't sum to 0, I know there's an error in the first column. If I look in the first row and it doesn't sum to 0, I know that there's an error in the first row. Imagine the red digit is wrong. We're going to assume there's only one error. If the red digit is wrong, then the first column sum is wrong. The first row sum is wrong. There's only one thing that's in both the first row and the first column. So I know the error has to be the red bit and I can correct it. Imagine that it's the blue bit in the first row that's wrong. Then the first column would be a correct sum. The first row would be wrong. There's only one thing that's in the first row that's not in the first column. It's that blue bit and I can correct. So by writing things geometrically like this, I'm still using the same number of check digits, but I have a really nice interpretation of what's going on. So here is a way to do 2 bits of information. So I put them next to each other, and I look at the first row and the first column and the second column. And if you just go through and you do all the cases, you will see that if you make a mistake, it will correct it. So what fraction of our message is information now? I'm sorry? Around, but exactly what? 40%. So we're still below the threshold that we're willing to consider acceptable at Michigan. Could you generalize this a little bit better and do better than 40%? What could you do next? Okay, good. So one thing is you could add 1 row above that, but let's say you're not as clever as you are. Yes, you could add another column. And so if we added another column here, we would have 3 bits of information and 4 bits of checking. And so if we do that, we can get as close to 50% as we want. We would never be there, but we could get a lot closer. All right, so you had a great suggestion of adding a row on top. So one of the things that I find interesting about these problems is it's not always clear what's the next best thing to do. So you wanted to add an entire extra row, right? So this is almost like the discovery from the real numbers to the complex numbers. A question?
How does it work to do red digit points are different? Like, would they like want to not check right?
So for which one?
So like if you're writing across the top row, like
Sure. So let's say the first pink is wrong and everything else is right. Then the first row doesn't sum to 0. The first column doesn't sum to 0, but the second column sums to 0. So I know there's an error somewhere in the first row. I know there's an error somewhere in the first column. And since there's only one error, we're assuming we don't have two errors, then it must be that pink dot, because that's the only thing in both the first row and the first column. So if you know your history of numbers, we have the real numbers, then we have the complex numbers, which is a degree 2 extension of the reals. What is the degree 3 extension of the reals? Oh, it got really silent. There is no degree 3 extension. What comes next? The quaternions, which is degree 4. And after the quaternions, octonions. And you start losing more and more math properties as you go higher and higher. That you don't always have nice examples for every little bit. So you basically said, you know what, Professor Miller, let's skip 3, let's go straight to 4 bits of information. So the question is, if I give you different amounts of data that we want to transmit, what's the right geometry to use to transmit it well? And you came up with a really good suggestion for 3. Is there a good suggestion? I mean, a really good suggestion for 4. Is there a good suggestion for 3? Does anybody know a shape that might work well for 3? Yes? Triangles. So here is 2 different ways of writing it. You know, the first is using triangles. The second is using squares. Which does a better job of transmitting information? And you can make an argument for either one. It depends on what your metric is. It depends on what you decide. You've got to be very clear about what your assumptions are and what your metric is. I can give an argument for either one. Can somebody give me an argument for one of them as to why it's better? Yes.
Does the one on the left catch 2 errors?
No, it will still only catch 1 error. Do we agree that they're both the same percentage of information? They're both 50%.
Yeah, let's say for the second one, if like you have a row that doesn't sum to 0 and you have a column that doesn't sum to 0, it can like sum to exactly where.
But we can do the same thing here. We have 3 lines. So both of them are able to pinpoint exactly 1 error. Which one is better?
I like the right one, bigger.
Okay.
On the other hand, the left one has fewer comparisons.
Ah, the left has fewer points. So the left gets you 50% without using as many points. Why is that valuable? Well, the more bits you have, the more likely you are to have that case with 2 errors. So by using 6 bits rather than 8 bits, it's actually a little bit better. There is, however, an advantage of the square over the triangle. So you are correct, but it's a question of exactly how do we want to phrase this. I think it's easier to code the square. And I think it's easier to generalize the square. I can still write down what's going on with the triangle, but for the square, what's the next number that we're going to do in terms of the number of bits that we can transmit of information? It's 9. And you know exactly how to set it up, right? And after that 16, you know how to set it up. You know, you just have an n by n square, and each column and each row has a check digit. Anybody want to guess how you generalize the triangle? What comes next? So it could be a hexagon. And so I strongly urge you to try to come up with ways to generalize. I found a way to write it down. And here's how I did 6 with the triangle versus 9 with the square. And so I added, lines for each one of them. And then I put my check digit, which is going to be taking the 3 midpoints of the sides, and I will add a generalized line. All right. So my lines are no longer straight lines, they're more now curves. And so if I do that, you can go through the argument and you can see it's exactly as good, and it uses fewer points. So right now, the square is still easier to code. Anybody want to try to guess what the picture would look like next? I have no idea, because I do not really know how to generalize that. There's a better way of doing it. And if you look at what I'm doing here, so this was the initial square I mean, the initial triangle over here. These next red dots at the ends were the initial data bits. They were I'm sorry, the initial check digit bits. What I did is I changed every check digit to a new bit of information that I want to transmit, and I extended the original lines. And then I added a new point on each line. And so the 3 points here are just the natural extensions. And then I have the continuation of just drawing a line through all of them. And so now if I wanted to go to the next level, I would take each blue bit and make it a pink bit, add another point on each of those lines, and then add a new line going through the check digits that I just converted to information digits. So when you do it like that, you can actually come up with a way to describe what you're doing. I still think the square is easier to code, and sometimes we're willing to accept a little bit of inefficiency for reasons like that. So you can calculate, for a triangle and a square, just what fraction of information you get, and then we can get as high of a percentage as we want at the cost of a longer string. So my question is, can anybody think of a better geometry to use? We had triangles, we had squares. I'm sorry? Sadly, I can't hear you. Excellent, a three-dimensional cube. And so, three-dimensional cube. Whoops. Yeah, okay. So here is, I did a two-dimensional cube and a three-dimensional cube. And so if you look at the two-dimensional cube, you can actually see a little bit of a center. You can see a little bit of the screw. That's my check digit. And then each plane, you'll have the white plane, the orange plane, the blue plane, the green plane, the yellow plane, and the red plane. Each one of those gives me a check digit. So for the 2 by 2 by 2, I'm going to have 6 check digits. For the 3 by 3 by 3, I have 9 planes. And each one of those gives me a check digit. So it's the center of each one of those. So if I do the 2 by 2 by 2, I use 8 data points, 6 check digits, 8/14 or 57%. That's at least enough for a success. If I do the 3 by 3 by 3, I'm actually at 75%. If I look at the 6 by 6 square, it just barely beats it. It's 77.8%. But things start to get much better as you keep going higher and higher and higher. If I use the 4 by 4 by 4, I now have 64 data points, 12 check digits, 84%. For the 9 by 9 square, it's only 81%. For the triangle, it's 83.54%. And so we can see with using fewer, yes?
In the 3 by 3 by 3 case,
Yes.
Is there a check digit accounting for the bit of information in the center of the cube?
Yes, because the one that's in the center is only in one color. So for instance, if I have the orange, blue, white, that's going to be in 3 planes. It's going to be the orange plane, the blue plane, and the white plane. And so you can, yes.
I'm so sorry.
Oh, no, okay. So if you go through, you can see, this is how, you never want to do algebra in public. But if you go through and look at all the different cases, you can see that there should be a way to assign the check digits to go through all of this.
Oh, I see. There's just a,
Right, because there's the slicing planes going through. Yes. Because that's coming over here. So excellent question. Except rather than a pyramid, what is this? Pentahedron or a megamix, depending on your knowledge of Rubik's cubes. And for this, you can see the little dots on the center, which will be my check digits. And you can start asking, what can I do with these shapes? We're now doing a class on applied platonic solids. Now, who knows what happens to platonic solids in higher dimensions? Yeah, things get very interesting in higher dimensions. So I urge you to look up and see what happens to platonic solids in higher dimensions. But we can still do the cubes as we go higher and higher and higher, along with another shape. So you could ask, what would you be able to do in situations like this? Anybody know how many points I have, how many pieces I have on this, on the left? I have 12 faces. Each face has 5 pieces. That's 60, but everything's on 3 faces, so I divide by 3. So I have 20 bits of information. So my question to you is, if you want a research project, which numbers allow us to have a nice geometry to transmit things? There's lots of other generalizations of this that you can do. If you've seen Hamming codes, how many people have seen Hamming codes? So I'm not going to go into too much detail. You can just look through this slowly at your leisure. Here is a way to transmit 4 bits of information with 7 bits. You have 3 check digits. And so in honor of Manhattan, I've named it Manhamming, where you have the blue subway line, the orange subway line, and the green subway line. So I've color-coded the check digits now. And so if something is wrong with bit that's labeled D1, then you would have an error in the blue, you would have an error in the orange, but the green would be okay. There's only one thing that's in both blue and orange, but not in green, and that's D1. There is a rhyme and a reason to why the points are labeled 3, 5, 6, 7 on top and 1, 2, 4 on the bottom. If we went further, anybody want to guess what the next number would be on the bottom? 1, 2, 4, 8, and then it comes with powers of 2. And so there's nice reasons as to why it works beautifully for 1 less than a power of 2. And so if you wanted to transmit on the order of 4,000 bits of data, we could see how well Hamming would do versus a square and a cube. And you can see the square does around 97%, the cube around 98.8%, Hamming is doing around 99.7%. It's a little bit better, but it's so good at this point that almost any of them are fine. And sometimes you'll actually make the trade-off of doing something that's a little bit easier to implement at a little bit of a cost. So I want to end with 2 fun things. The first is, say you want to transmit this following string, which is an extremely important string. I don't have time to explain why, but we want to transmit this. And I'm assuming that my errors in the blocks that I transmit, that it's very rare to have more than 1 error. How might you have an error? Gamma ray burst, right? Incredible Hulk. We have something going on, and it could be some event that creates some static or some noise. And if that happens, it's unlikely that it's going to be spread out, at very large gaps. The noise is going to be localized. So over here, I have 3 bits that are wrong, and they are 3 out of 4 consecutive bits. 1 bit actually got flipped twice and ended up back where it started. So if I have a method that assumes that I don't have 2 errors in quick succession, I'm going to have a problem here. There's a really beautiful way to solve problems like this. And this is one of the things I love about the subject. You don't need advanced graduate level classes. You need the ability to think in new ways, to think creatively. So instead of transmitting the message sequentially, what we do is we break up the message. We transmit every 4th bit. And of course, in practice, you might do it not every 4th, but maybe every 100 or maybe every 1,000. The disadvantage is you can't transmit until maybe the whole message and break things up like that. So you're not getting things sequentially on the other side. You'll have to put it back together. But that's fine. We have smart computers on both sides of the transmission. We can put messages back together. And if I split it up like this now, notice that the burst is now split into 4 different strings and no longer matters. All right, so we have on the order of 5 minutes left. And so what I thought I would do is talk a little bit about steganography. Is anybody familiar with this word? All right. What is steganography? Can you define it? So steganography is the art of hiding messages in messages. So what do you see? A tree. Now, if you had read the title, what could you say you saw? A cat. All right, now, of course, I might ask you, where's the tree that you see? Well, I probably won't ask that. I think even I, with my bad vision, which is going, can see that. But if I asked you, where is the cat? If I asked you, where is the cat? Does anybody see where the cat is? $100. Anybody see the cat? All right. Do you want me to show you where the cat is? Yeah. So let's talk a little bit about how do you transmit an image. So let's imagine I have an L by W grid with L times W pixels. So each pixel is a red, green, blue triple. We normally do from 0 to 255. We do like a power of 2 because we love powers of 2. So if we have 256 possibilities for each one, when you look at how many different color pixels we have, it's almost 17 million. How many people know at least the names of 4 different colors? 10 colors. You can name at least half of a 64 pack from Crayola. I think I could probably do it. How many can do 100,000 different colors? This is Midnight Jungle Blood Moon, something like that, right? Do we really need to be able to transmit 16.7 million colors? Can we give up a few? All right, so let's look at it this way. How many of you have seen Taylor series? Okay, so instead of expanding a number as constant times x squared times x cubed, we can do things in other things. Binary or decimal, we're writing 2021, 2 times 1,000 plus 0 times 100 plus 1 times 10 plus 2 times 1. It's just another expansion. What I can do is I can expand my red, green, and blue tuples in binary. And so I'm going to let the r's be the digits. So r0 is the constant term, r1 is the power of 2, and so on and so on and so on. So if I were to just change r0, I would move my number by at most 1. Well, 1 out of 256, that's not a huge amount. If I were to change just the last 2, how much could I move by? 3. Maximum movement is 3. That's not that much. If I just change the last digit for all of the tuples, that gives me 8 colors to play with. If I change the last 2 digits, I have 64 colors to play with. That's enough for a reasonable Crayola pack. Now, I'm not going to get the 128, but 64 is not bad. There's a lot I can do with 64 colors. So what you can do is if you just change the last digit or 2, either of just one of the colors red or all 3 of them, you can hide messages. Imagine you want to write a message to somebody and you have a white screen and you have black text. So we'll say a black dot is 1, a white dot is 0. So now you just change your last digit, your R0, to be either 0 or 1, depending on the message you want to transmit. And you've now encoded that, you've now hidden that message in the image you're sending. If you want to do something more involved than that, you can change the last 2 digits, you can play with colors. The danger of this, of course, is that you might be able to recognize when you receive the image that something is wrong. And then you might run some data diagnostic programs and actually check. And so I have actually done a lot of work in the last couple of years using Benford's law to detect fraud. And you can use stuff like this to detect when there are some issues with image data. There are other places where it's been tried to be applied which had less success, but in image data, you can sometimes detect that something has been changed. One thing you could do is you could have a agreed upon method. Sometimes people have a favorite sonnet or poem or book that they use, and you can use information from that to tell you which bits do you change. And so what you might do is maybe you use the length of the word to tell you how far you have to go to the next bit that's been changed. And if you do something like that, as long as you have an agreed upon secret, you might be able to hide something like that. So in terms of, here is the tree. Oh, dramatically. Okay, there's the cat. The cat is hidden in the entire picture, just done by choosing some of the bits. Does that look like a great picture of a cat? No. It's not the greatest picture of a cat. Does that look like a good picture of a tree? Yeah, I think it's actually a decent picture of a tree. The cat could be better. But when you're not using that many colors, it's not surprising. And then, of course, you have an interesting optimization problem. How much do you want to devote to the cat? How much do you want to devote to the tree? You need to do it in such a way that people don't have a sense that you've changed anything. Right, so thank you very much. And then if anybody has any questions, happy to chat.
Anyone have any questions for Professor Miller?